This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to begin our study of physics, and specifically, we start with the area of physics known as mechanics. Mechanics is the area of physics that's concerned with motion. We break mechanics into some subgroups, and today we're going to be starting with kinematics. In kinematics, we describe motion. We are going to define terms such as position, displacement, speed, velocity, and acceleration. We'll learn how these different quantities are related to each other, and that's going to allow us to solve some basic motion problems. A little bit later on in the course, we'll be looking at dynamics. In dynamics, we study forces and how forces affect motion. In this course, we're going to concentrate on motion in only one dimension. That could be either horizontal or vertical. So in other words, our car here, it might be going to the right or to the left, but it's not going to do more than that. In the same way, our baseball here could be going up or down, but what we're not going to study in this course is more complicated motion, which is called projectile motion. For example, where we shoot a ball, or let's say a cannonball, in some way and it goes in a path like that. To start out here, the first thing we have to be able to do is identify where an object is. And that's what we mean by the position of an object. One of the ways to do that is by setting up a one-dimensional coordinate system. Here in the diagram, I've got a one-dimensional coordinate system for the x direction. And let's say that we have a person and they start out at the 50-meter mark. I'm going to denote their position with the symbol x and then a little subscript 0 here. And we call that a naught. So naught, it just is another word for 0. So that would be called x naught. And in this case, x naught, the initial position would be 50 meters. Whenever you see a naught, that means initial. So naught means initial. Now let's say our person walks down here to the 0 position, and then they come back and they end up at the 10-meter position. So we would say their final position is 10 meters. Notice that for final, we just use an x with no subscript. So if there's no subscript, it means final. If there's a naught, then it means initial. Okay, so now we know how to specify where an object is. We just need a one-dimensional coordinate system to do it. The next thing we want to look at is distance. Now, we're all familiar with the basic concept of distance, but just to make it a little bit more concrete, let's look at how far did this person move? What distance did they move? Well, we can see they went from the 50-meter line to 0, so that's 50 meters. And then they went an additional 10 meters. And so we would simply add 50 meters and 10 meters and say the distance that that person moved was 60 meters. Now, we're all familiar with the concept of distance. The next thing we're going to define, you may never have heard before, and that's the concept of displacement. We define displacement in the following way. First of all, we use the Greek letter delta, and we write it as delta x. You may remember from math that delta means change. And so the way we define the displacement of an object is its change in position. In other words, what was its final position minus what was its initial position. So again, remember that if there's no subscript, it means final. And if there's a naught, it means initial. In general, and you may remember this from math, delta always means take the final and subtract the initial. So let's figure out what the displacement of this person was for this motion. you'll notice that their final position was 10 meters, and their initial position was 50. And so 10 minus 50 is negative 40 meters. The first thing we'll notice is that that's a very different result than what distance they went. The other thing is we notice that here we get a negative sign, and that negative sign has significance. What it means is that the person ended up to the left of where they started. So a negative displacement means the person ended up to the left of where they started. If the displacement had been positive, it would have meant they ended up to the right. Displacement, it turns out, is an example of something called a vector, and we're going to talk about what we mean by that. Distance is a scalar. So we need to talk about what do we mean by a scalar and what do we mean by a vector. When we talk about scalars and vectors, what we say is that a scalar has just a magnitude, whereas a vector has a magnitude and direction. Now the word magnitude might be a little confusing. Magnitude just means a number. So a scalar can be specified just by a number, whereas a vector needs both a number and a direction. And it turns out that in physics we find we have these two different types of quantities. Some quantities just require a number to specify them, but other quantities require both a number and a direction. So just to make this a little bit more concrete, let's go through some examples and try to see what quantities are vectors and which are scalars. By the way, for vectors, in one dimension, if it's positive, it just means to the right, and if it's negative, it means to the left. Or if we're talking about vertical motion, up would be positive and down would be negative. Vector or scalar. You might want to actually pause the video here and think about these quantities and think, do any of these quantities require you to give not only a number, but a direction to completely specify that quantity? Okay, well let's go through them. Time is a scalar. In other words, if you ask me, what time is it? I'm going to say something like 3 p.m. I'm not going to say 3 p.m. to the right, or 3 p.m. up, or 3 p.m. down. It doesn't make any sense to give a direction with time. When we need to specify what time it is, we just need to give a number. So time is a scalar. How about temperature? Well, temperature is also a scalar. Because again, if you ask me, what's the temperature in this room? I might say it's 75 degrees Fahrenheit or 20 degrees Celsius. But I don't need to give a direction along with that. It wouldn't make sense to say 25 degrees to the right. How about mass? Well, mass is also a scalar. So mass is measured in grams or kilograms, and we actually use kilograms in physics. But there's no direction to mass. Mass, as we'll talk about more in an upcoming video, is just a measure of how much stuff there is in an object, and there's no direction to that. But now let's look at position. Imagine that you are standing here, and we'll put you at the origin of our scale, or of our coordinate system, I should say. And let's say that I tell you that there is a package that is 2 meters away from you. So I'm telling you the position is 2 meters. Well, you need to know if I mean that it's 2 meters to the right or it's 2 meters to the left. And again, here we would call that a positive position if it's to the right. If it's to the left of our origin, the position would be negative. And so I need to know, is the object to the right of me or to the left of me? And therefore, position is a vector. We don't just need a number, we need a direction. Should I move 2 meters to the right to pick up the package, or move 2 meters to the left? Force is another example of a vector. And this one's pretty easy to understand. If you just have an object, let's say, in front of you on your desk, and if you take that object and you push it away from you, so you exert a force on it that's away from you, you get a very different result than if you pull it towards yourself. You exert a force on it towards you. So clearly with force, it's not enough to just say how hard you're pushing, but you also need to know the direction. Position and force are vectors. The next quantity we want to define is called average speed. And you're all familiar with the concept of average speed. It's just how far did you go in how much time. Speed is a scalar. It doesn't have direction. And so let's use the example that we started with earlier. We had our person who started on the 50 meter at the 50 meter position, and they went all the way to 0, and then they came back to the 10 meter position. Let's say that they did that in a time, delta t, of 10 seconds. Well, let's figure out what their average speed was for that motion. You'll notice all I have to do is take the distance they traveled. So again, the person went 50 meters, plus they went an additional 10 meters. And we just want to divide that by that time interval, how much time it took them to do it. And you'll notice that we have 60 meters per second, or sorry, 60 meters divided by 10 seconds, or 6 meters per second. That would be the person's average speed for that motion. Now, in everyday speech, we often interchange speed and velocity, but in physics they mean different things. Velocity is a vector, and the way we define average velocity is we define it as the displacement divided by the time interval over which the motion took place. So let's look at what the average velocity was for that person going through the same motion. So again, starting at the 50 meter point, coming over here to 0, and then ending up at the 10 meter position. And again, we'll say that the amount of time it took for that to happen is 10 seconds. Well, remember here we already figured out that the displacement would be 10 minus 50, or negative 40 meters. The time is 10 seconds. And so what we get is negative 4 meters per second. That would be the average velocity. You'll notice that's very different than what their average speed was. Now, we say that velocity is a vector. Again, in one dimension, the way we know whether something is to the right or to the left is if it's positive or negative. So notice that what this negative sign here represents is that the person moved to the left. If you make up your own example where they start out, let's say over here somewhere and end up over here somewhere, you'll notice that the average velocity is going to be positive. So a negative velocity means that the person moved to the left. Also, you'll notice that the average velocity doesn't really give us the details of what happened. It's just basically saying that if you went negative 4 meters per second for 10 seconds, you'd end up 40 meters to the left of where you started. Notice this bar. That bar means average. In our example, it says a student rides her bike from her home to college and then rides back home. The distance from home to college is 11 miles. And then we've got a number of questions to answer. One of the things that I'm always going to do when I do a motion problem is I'm going to draw a diagram. So I've got my home, and I'm going to just set home to be where the origin is. You can always just set the starting position to be x naught equals 0. So my initial position at home is just 0. And so here's we'll put our person here. And our person now is going to go to college. We're told that college is 11 miles away. And so our position here would be 11, and we'll use mi, remember, for miles. So here now our student is at college. But we're told that they actually go all the way there, and then they come back home. So what was the total distance for the student's round trip? Well, it's just 11 miles to college plus 11 miles home. So we get 22 miles. What was the displacement for the round trip? Well, you'll notice that her final position is actually not 11 miles. That's where she is right here. But her final position is actually also 0 because she both starts and ends at home for the round trip. So the displacement delta x would just be final position minus initial position, but that's 0 minus 0, which of course is 0. So her final displacement is 0. She ended up right where she started. If the trip took a total time of 2.5 hours, what was her average speed? Well, we know that average speed is just the distance traveled per time. And so she traveled 22 miles, and she did that in 2.5 hours. And so we just need to do that on our calculator, and what you'll find is that you should get 8.8 miles per hour. And again, remember in physics, we don't use mph for miles per hour because we reserve m for meters. And so we're going to write that as mi over h for miles per hour. Now, her average velocity is the displacement over the amount of time the motion took. But you'll notice here that the displacement was 0, and therefore her average velocity was 0, simply because she didn't end up to the right or to the left of where she started. She ended up right back in the same place. Let's do a quick unit conversion review. We covered unit conversions in an earlier video. So why don't you go ahead and pause the video and do this problem, and then restart the video and check your result. Okay, so we want to convert miles per hour to meters per second. So you remember how we do unit conversions. I'm going to write the initial value, miles per hour, and I like to use brackets around these. And then I always want to just kind of keep in mind, where am I trying to end up? I'm trying to end up with meters over seconds. So I've got to get rid of miles to end up with meters. Notice that I've got this conversion that 1 mile is 1,609 meters. So I know that I've got to have miles on the bottom and meters on the top, because that way the miles will cancel out and I'll end up with meters. So I've got 1,609 meters over 1 mile. Now I'm going to keep going here because I can do multiple conversions at the same time. I want to end up with seconds in the denominator, but right now I have hours. So I know I need to get hours up here in the numerator so that they will cancel. And I have that 1 hour is 60 minutes. But then I got to do the same thing to turn minutes into seconds. So I know that 1 minute is the same as 60 seconds. Okay, so I'm going to just stop here and make sure this makes sense to me, and you want to make sure it makes sense to you. Notice that now I can see miles is going to cancel with miles, hours cancels with hours, minutes with minutes, and you'll notice the only units we're left with on the top are meters. The only units we're left with on the bottom are seconds, and so we're going to successfully have converted to meters per second. Now in terms of the math involved here, you'll notice I'm just going to take 60 and multiply it by 1609, multiply it by 1, multiply it by 1, and then I'm dividing that by everything on the bottom. So I have 1 and 60 and 60. And so you can just do that on your calculator. If you want to make it a little bit easier for yourself, you'll notice you've got a 60 on the top and a 60 on the bottom. And of course the ones don't have any effect, so that really you're just taking 1609 and dividing by 60. And our final answer is going to be 26.8 meters per second. We have one more quantity that we need to define, and that is acceleration. Average acceleration is defined as the change in velocity per time interval. Notice again that because we're talking about average acceleration, we have the bar over the a. And so that bar, again, always means average. Notice too that with v and v naught, these are different. We know that v with a bar over it means average velocity. But here we have v and v naught. V would be the final velocity. In other words, how fast is the object moving at the end of the motion? And v naught would be the initial velocity. So again, we're using no subscript to mean final and naught to mean initial, just like we did with x and x naught. And again, we could write that in a shorthand way by using delta notation, that it's delta v over delta t. Okay, so let's do a quick example here. Let's say that I tell you that the average acceleration is 5. Well, we've got to figure out what the units are. We know that the units of velocity are meters per second. We know the units of time are seconds. And so one way that we could write our units for acceleration would be meters per second per second. And it turns out that's actually a really good way to think about the units for acceleration. Because what acceleration is telling you is simply how much is the velocity changing for every second. So let's just do a quick example to see what I mean. Let's say that at t equals 0, so at our starting time, our object is not yet moving. Let's figure out how fast it's going after 1 second. Well, if the acceleration is 5 meters per second, that's simply telling you that for every second that goes by, the velocity changes by 5 meters per second. So after 1 second, our velocity will be 5 meters per second. But after another second goes by, so after 2 seconds total, notice another second has gone by, the object has gained another 5 meters per second of velocity. So we'd have 10 meters per second. Or after another second goes by, our object would now be going 15 meters per second. So that's what acceleration means. It's just how much is the velocity changing for each second. Now it turns out there's a shorthand way to write these units of meters per second per second. And I want to just show you how we come up with it. Here we're going to just use the basic ideas of fractions. We know that meters per second, that's already a fraction. I'm going to write seconds as seconds over 1. So now that's written as a fraction. And remember what we do to divide fractions. We take the reciprocal of the denominator and multiply it by the numerator. In other words, we take meters per second, the numerator, and to divide by seconds over 1, we would multiply by the reciprocal, 1 over seconds. So meters times 1 is meters. Seconds times seconds is seconds squared. And so when you see accelerations written, you'll usually see the acceleration written as meters per second squared. So the average acceleration is 5 meters per second squared. But always remember that that's really just a shorthand for this. And really, this is the better way to think about it, because it reminds you that acceleration is just how much the velocity changes for every second. Let's look at an example. A car accelerates from 0 meters per second to 50 meters per second in 10 seconds. What was the acceleration? Well, we know that average acceleration is defined as delta v over delta t. And we can write that as v minus v naught. So again, final minus initial. And delta t, I could write it as t minus t naught, but we always set t naught equal to 0. So delta t is just going to be the total change in time, which is just going to be 10 seconds. So I'll just leave that as delta t. So we have our final velocity is 50. Our initial velocity is 0 divided by 10. And so we get 50 over 10, or 5. And I'm going to first write it as meters per second, or 5 meters per second squared. So how fast was the car going after each second? Why don't you figure that out up through 10 seconds, and then once you figured that out, restart the video and just make sure you got it right. All right, so I'm going to just make a little table like we did on the previous slide with t and v. So if the object was not moving when we started, which it wasn't, then again, what this 5 meters per second squared means is that for every second that goes by, we gain 5 meters per second of velocity. So after 1 second, it would be going 5 meters per second. After 2 seconds, it would have gained another 5, so 10 meters per second. After 3 seconds, 15 meters per second. So notice that for every second that goes by, we're simply gaining 5 meters per second of velocity. So after 4 seconds, we'd be up to 20 meters per second. 5 seconds, 25 meters per second. 6 seconds, 30 meters per second. And I think you probably can see the pattern here. So at 7, we'd be at 35 meters per second. 8, we'd be at 40. 9, we'd be at 45. And finally, 10 seconds after the car started accelerating, we'd be up to 50 meters per second. Let's look at an example of what happens if the acceleration is negative. Well, if you think about it, if the acceleration is negative, it means we're taking away velocity every second. So for example, let's say that we have a car, and our car is initially moving at 30 meters per second. And let's say that the acceleration, the average acceleration, is negative 5 meters per second squared. So what does that mean? It simply means that when t is equal to 0, our car is moving at 30 meters per second. After 1 second, that velocity is changed by negative 5 meters per second. Because again, negative 5 meters per second. And so after 1 second, it would be going only 25 meters per second. Or after another second has gone by, it would be going only 20 meters per second. If the velocity is positive and the acceleration is negative, it simply means that the object is slowing down. Now in the next video, we're going to look at some equations that make it easier to solve for some of these quantities in terms of other quantities.